Hello, this is Mr. Warren. We'll go over the extra credit project for the option for the end of the year. A lot of it will just involve taking some screenshots of cool graphs, but we'll explain first where the Mandelbrot graph set comes from. Imagine, let's see, there we go. This is a picture from the movie where they found a secret message on the back of the U.S. Constitution. They found a secret code there. But what if there was a secret code also hidden inside of numbers? And that's what we're going to talk about today. It's a secret inside of numbers that no one knew about until 2 years before I was born in 1980. So we're going to talk about the Mandelbrot set. What is a set? A set is just an exclusive club for numbers. For example, an easy kind of a set would be the set of even numbers. So all the numbers that are even numbers get to come into the set, and all the numbers that are not even numbers do not. So 2, 4, 6, 8, 10, those all get to come into the even number set, but 1/2, 5, -3, those do not get to be in the even number set. But we're going to look at the Mandelbrot set, which is a little bit more complicated to figure out which numbers are in and which numbers are not. Here it is. We're going to look at this here. Now the formula for this is, it looks weird because it's a bunch of weird math symbols. Z to the n squared plus c equals z to the n plus 1. Now this did come up a little bit in Algebra 1 and Algebra 2, but what this means is it's when you make a list of numbers, and this number tells you how to take the last number in order to get the next number. So what this is basically saying is, to get the n plus 1 number, to get the next number, you go to the old number and square it and then add something else. And the plus c is what we're testing to see whether or not all these different kinds of numbers for whatever c is this time can make it into the Mandelbrot set. And it does make it into the Mandelbrot set if the numbers stay small. But if the numbers get big on your list, then they're not in the Mandelbrot set. So let's test c equals 1, for example. Because if you have like the set of even numbers, it's easy to see what's an even number. If you have the set of negative numbers, it's easy to see what is an even number. But with this one, it's hard. Even if you're good at math, you can't really tell until you plug it in and try it out. If you try c equals 1, we always start with 0, so we'll start with 0. This time we made c1 plus 1. What's that? So that is 1. So our list here is 1. Then we take the 1 and plug that in. 1 squared plus 1 is 2. So our next number is 2. Then we take that and plug that in. 2 squared plus 1 equals 5. Next number is 5. Then we take the 5 and plug that in. 5 squared plus 1 equals 26. And you could go on, and I think that's 677 or something like that. So these numbers are not staying small. So we're going to say no, 1 is not in the Mandelbrot set. Just to try a different number, let's test c equals -1. So we'll start with 0 again. 0 squared minus 1 equals -1. -1 squared minus 1 equals 0. And then you just get stuck in a loop where all the numbers in your list are -1, 0, -1, 0, -1, 0. So this list does stay small. So yes, it is in the Mandelbrot set. So that's a little bit of background with so it's tedious, isn't it? It's not that hard to do, but it's not fun to do. And that's why with computers and calculators, it got a little bit easier to figure out what is in this set and what is not. And if we made a number line, you could have your 0, and you could have 1, and you could have -1. And -1 is in the set. 0 is, but 1 is not. But there's also other kinds of numbers you can test as well. They're called imaginary numbers. Now, I don't like that term necessarily, but it's what they're called because they do exist. They're just so weird we don't see them very much. As you probably learned from your math class at some point that the square root of -1 equals I. So I squared is -1. So what that means is that it's not negative or positive, because if you have a positive number squared, your answer is positive. But if you have a negative number squared, your answer is still positive. But if you have an imaginary number squared, then you get a negative number. So it's called imaginary because it's so weird and unusual. It's a number that's not positive or not negative. So where would you graph that? If it's not positive or not negative, you could add another axis to the plane. And you could have this being 1i up there and -1i down there. And so then you could even have complex numbers that you graph and test it to see if it's in the Mandelbrot set. For example, this number here would be 1 plus I. And this number down here would be 1 minus I. And so you could test all of these and graph it in. So what happened when, like I said, this was discovered in 1980. When we started plugging that in, what we got was this kind of a weird shape. And they thought that was very unusual, so they checked it more and more closely. And when you got a higher resolution, this is what the graph looked like. And so this is that secret that's hidden inside of numbers that we didn't know about until 1980. Is that it's a infinitely squiggly, you could say. The surface area of this graph is infinite. So if you had a paint can shaped in this shape, you could carry around some paint in that paint can. But even if you had 10,000 of those paint cans, you couldn't paint the outside of just one of them because it squiggles so much that it's the surface area is infinity. You could look at it here, and this will be the website that you'll use to play with these a little bit too if you want to try the extra credit project. This is the shape of it, and you could see it's a cardioid, kind of like a heart shape. No one knows why it's a heart shape, just one of those mysteries of the universe. And if you zoom in, this is you could see that there's, let's bring it down a little bit to 500 iterations. You can see there's a baby one here. And if you zoom in more, you can see that there's another baby one here. And if you zoom in more, you can see that there's another baby one here. My computer's maybe not strong enough to get all the details in, but if you had a stronger computer, you could zoom in forever and forever and forever, and it never ends with slight variations. One thing about fractals is you can't even tell how zoomed in or how zoomed out you are. I think, okay, I'm finally zoomed out again. There's a couple features you could see. If we go over to the right side of the heart here, what we see is called the Valley of Elephants. Can someone get the door in this case? Here's the Valley of Elephants. And because you can see it kind of looks like an elephant on a ball. And you could even zoom in on them. And if you zoom in on the elephants, you get more of the Mandelbrot shapes. And you get interesting shapes all over the place. Let's try to increase the iterations there. And you get these webs that go on. And you could zoom in on these infinitely and get more and more variations. That was a little peek at the Valley of Elephants. If we, it's pretty cool looking. If we zoom out again and look at another part, let's go over to the other side of the cardioid and look over here. This side is where you can see the Valley of Seahorses. You got these webs in the middle here, and you could zoom in on that web for forever and forever and forever and get an infinite amount of detail. Or you could go off at one side of the web and then find more of those shapes again. So we'll try to zoom out. of the webs out of the Valley of Seahorses. And if you go a little bit to the left to the other side here, it's kind of like the double galaxy spiral galaxy. And this the line of this graph, this line that is the border between what is and what is not in the Mandelbrot set, is so intricate that it's actually a double spiral on right next to each other. You kind of see that the double spirals there, and more infinite complexity that goes on forever and forever and forever. So when you zoom in with this, you could see all kinds of different things. So I'll refresh this to bring it back to the default. And you can see we have exponent of 2, because what that exponent of 2 means there is that we did our formula of x squared plus 1. We did, then repeated that over and over again. You could change the formula because there was nothing special about the formula, just hidden in numbers. If you made it x cubed instead of x squared, you might want to play around with the exponents a little bit. Then you have a double bulb. And let's check over at our Valley of Elephants when you have x cubed. In the Valley of, we had an infinite number of elephants before, but now there's twice as many as infinite. And now the elephants, instead of elephants on a ball, there's 2 elephants on a heart. No one knows why. Just a mystery of the universe. And if you change it to x cubed, then you get a triple cardioid. If you change it to x to the power of 5, you get a quadruple cardioid. And if you change it to x to the power of 6, you get a 5-way cardioid, like a good luck clover there. And if you change it to x to the power of 7, then you have a 6-way cardioid. And the reason why I brought here is because it's a snowflake. This is exactly what snowflakes look like. When you zoom into snowflakes, they also look fractal-like. But with snowflakes, when you zoom in too much, they get blurry, or it changes because, when you have physical atoms, you can only zoom in so much. But with fractals, with the math equation, you could zoom in infinitely forever into, so this is kind of like an infinite snowflake there. I'll once again default back to the normal one. So that's what that looks like. So your assignment will be to find some interesting spots and take some screenshots. And if you submit your screenshots to me, it might become things we hang up around the classroom. And another feature is that the graph knows how to count. If you look at how many branches are on each little bulb going off, it goes 3, 5, 7, 9, and counts up all the odd numbers up to infinity. And on the other side, it counts all of the even numbers up to infinity. And the graph also knows how to add. If you look at the bit in between the 5 bulb and the 3 bulb, there's an 8 bulb. So even in between, you could zoom in infinitely, and it adds up those numbers for you all the way up to infinity in between each of those. Like I said, fractals exist in nature as well. There's a weird correspondence between math and some of the things we see in nature that has this fractalness where you zoom in more and more and more, and you can't even tell how zoomed in you are. This is the frost on a window. This is a fern. A fern could be a fractal because one little leaf is the same shape as the whole branch. This looks like a fractal, but it's just a coastline. This looks like a fractal graph, but it's actually just mountains from Google Earth images. Some mountains in Alaska, near where my brother lives. This is, on the left, it's a fractal from the math equation. On the right, it's a fractal from a lightning bolt. Here you can kind of see that lightning fractals like that. And here's that comparison of that snowflake in the math and the snowflake in real life. And here's the comparison of the spiral from the fractal and from looking into a telescope. And again, it's just amazing, and no one knows why this happens. This is a good math paper about this called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He wrote in his paper, "It is difficult to avoid the impression that a miracle confronts us here, or the two miracles of the existence of the laws of nature and of the human mind's capacity to divine them." So it's saying that we don't even know why math is so good at describing the world. The miracle of the appropriateness of the language of math for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. But so it's some mysteries. Like I said, we don't even know this existed until very recently, and we still don't even know why it's there. But this beauty did not come from the computer. It did not come from me. I just found it. It didn't come from the math equation because you could change the equation and it's still there. Just a mystery that hidden inside of numbers is the fractal. But have fun finding cool parts and send me your screenshots. Thanks.